Okay, students, so let's get started with today's chapter or today's past paper. You can say that is A2 Physics past papers regarding ultrasounds. So, chapter number 13 is of medical physics, and we have a subtopic in medical physics by the name of ultrasounds. So, let's start with the past papers of ultrasound. Okay, so describe how reflected ultrasound pulses may be used to obtain diagnostic information about internal structures. So, how are reflected ultrasound pulses used to obtain information about internal structures? Very, very easy. The time delay, or you can say interval, or you can say the time difference between the ultrasounds generated between the ultrasound generated and ultrasound detected and ultrasound being detected. The time difference between the ultrasound being generated and ultrasound being detected gives us the depth, gives us information about the depth, gives us information about the depth, about the depth. Secondly, the intensity of ultrasound, the intensity of ultrasound gives us information, gives us information about the nature of the object, about the nature of the object. Simple as that. Okay, let's move on to part B, I1. Define a specific acoustic impedance of a medium. Yes, what is a specific acoustic impedance of a medium? What is Z? A specific acoustic impedance of a medium is the product of density of a medium and what is the second thing? And the speed of ultrasound in that medium. Speed of ultrasound in that medium. So basically Z is equals to what? Z is equals to density into speed of the ultrasound. Simple as that. Let's move on to part I2. Table 10.1 shows some data for water and for glass. Okay, these are some data for water and glass. Determine the intensity reflection coefficient. We have to determine alpha for ultrasound that is incident on the water glass boundary. So first of all, tell me what is alpha equal to. Alpha is equal to Z2 minus Z1 whole square divided by Z2 plus Z1 whole square. Okay. How will I calculate Z2 and Z1? Very, very easy. If I multiply this density with this speed, Z1 will come out to be what? Z1 or Z of water will come out to be what? 1000 multiplied by 1420. That is equals to 1000 multiplied by 1420. This comes out to be 1.42 into 10 raised to the power of 6. Okay, what will be your Z of glass? Z2 or Z of glass will be equal to what? 2500 into 4560. Let's calculate that. 2500 into 4560. This comes out to be 1.14 into 10 raised to the power of 7. So you have Z2, you have Z1. Let's calculate alpha. 1.14 into 10 raised to the power of 7 minus 1.42 into 10 raised to the power of 6 whole square divided by what? 1.14 into 10 raised to the power of 7. plus 1.42 into 10 raised to the power of 6 whole square. Okay, let's calculate this answer. Minus 1.42 into 10 raised to the power of 6. Let's take a whole square. This is a... Let me carefully put this in the calculator so that I make no mistakes. Answer plus 1.42 into 10 raised to the power of 6. To square this entire thing, you will get a value of... Yeah, your value comes out to be 0.6. 0.61 till 2 decimal places. So this marks our end of the first question. Let's verify it as well. Same as marking scheme. So that's good. That's good with our confidence. Let's move on to this one. Table 8.1 shows some data relating to the properties of air, okay, gel and body tissue. Okay, so these are some properties for air, gel and body tissue. Okay, the data are given to 3 significant figures. Okay, so the data is given to 3 significant figures. Show that the specific acoustic impedance of gel is this. Okay, you have to show that for gel, the Z of gel is equals to this value. So how do we calculate specific acoustic impedance? Very easy. Density into the speed. What is your density? 1200. What is your speed? 1400. Multiply both of them. 1200 into 1400. This comes out to be what? This comes out to be 1.68 into 10 raised to the power of 6. We have proven that. And obviously you can write the units as well. kg m minus 2 s minus 1. Okay. Let's further move ahead. Complete table 8.1 by calculating the missing values to 3 significant figures. Use the space below for any working you need. Okay. So we have gotten this value, that is 1.68, 10 raised to the power of 6. Let's calculate the other values. So for air, you can write this. For air, your specific acoustic impedance is 440. Your speed of sound is 340. Can you calculate the density? Yes, 440 divided by 340 is equals to your density. Let's calculate density. 440 divided by 340, this comes out to be 1.29. Let me see how many significant figures we have to give. 3. Okay, so we have to give our answer till 3 significant figures. This will become 1.29. Let's do the same thing for this tissue. Where should I put this working? Let's put this working of air here, and let's do it with a different color. The specific acoustic impedance of tissue is what? 1.68 into 10 raised to the power of 6. One surprising thing I see here is the specific acoustic impedance of gel and tissue are both same. These two values are same. Let's see how we will utilize it in the coming questions. Z of tissue is equals to density into speed. 1.68 into 10 raised to the power of 6. Density is 1090 multiplied by C. C comes out to be what? 1.68 into 10 raised to the power of 6 divided by 1090. Let's calculate it. 1.68 into 10 raised to the power of 6 divided by 1090. This comes out to be 1540. Since we have to give our answer till 3 significant figures, this will do the job. Okay, use the information to calculate intensity reflection coefficient for air tissue boundary and the gel tissue boundary. Okay, so we have to calculate alphas for both of these. So let's first of all calculate alpha for air tissue boundary. So what is the, we have to calculate the alpha for air and tissue boundary. Okay, so what is the specific acoustic impedance? Let's say this becomes your Z2. Let's say this becomes your Z1. So let's write it here. Z2 is 1.68 into 10 raised to the power of 6. I hope I have written it correctly. And let's say Z1 is 440. Now you have to calculate alpha. What will you do? Z2 minus Z1 whole square divided by Z2 plus Z1 whole square. Okay. Now let's just plug in the values. Nothing complicated. Let's just plug in the values. Z2 is 1.68 into 10 raised to the power of 6 minus Z1 is 440 whole square divided by 1.68 into 10 raised to the power of 6 plus 440 whole square. Okay. Let's put this in the calculator. 1.68 into 10 raised to the power of 6 minus 440 whole square and 1.68 into 10 raised to the power of 6 plus 440 into plus 440 into whole square. This comes out to be 0.998, and if I have to give it till 3 significant figures, let's say it will be 1.00. Okay, so yeah, if I want to give it till 3 significant figures, basically let me write the 4 significant figures first of all. It is 0.9989. So if I want to give this value till 3 significant figures, this will become 0.999. Yeah, you can keep it like this if you want to give it till 3 significant figures. However, if you convert it till 2 significant figures, then it will get, this is your 3 SF answer. However, if you want to give it till 1 SF, then it will 2 SF, then it will become this, because these are 3 nines that will get rounded off to 1.0. Now you have to calculate the alpha between gel and tissue. Okay, so your Z2 now becomes what? You can take anything as Z2. Let's say I am keeping my Z2 as the Z2 of tissue. 1.68 into 10 raised to the power of 6. My Z1 is the specific acoustic impedance for gel, that is 1.68 into 10 raised to the power of 6. Where did I got this from? Here. This is my specific acoustic impedance for gel, or you can say Z1 for part I2. Let's calculate alpha now. Z2 minus Z1 whole square. Now if you are a little smart, you wouldn't even want to do this calculation. Z2 is 1.68 into 10 raised to the power of 6 minus 1.68 into 10 raised to the power of 6 whole square. This entire thing will become 0. 10 raised to the power of 6 plus 1.68 into 10 raised to the power of 6 whole square. This becomes what? 0, because this numerator will cancel out. The answer will come out to be 0. Simple as that. Okay, let's further move ahead. Use your answer in B to explain why gel is applied to the skin during ultrasound scanning. Why is gel applied to the skin during ultrasound scanning? Very, very easy answer. See, this intensity reflection coefficient or alpha tells us how much of ultrasound is reflected. Okay, sir, how does this tell us how much ultrasound is reflected? How does the value of alpha tells us how much of ultrasound is reflected? So the higher the value of alpha, the more ultrasound is reflected. Now if you can observe when there was no gel being applied, the value of alpha was 0.99999. That means all of the ultrasound was almost reflected. So you can write here, when no gel was applied, No gel was applied. Almost all of the ultrasound was reflected. Ultrasound was reflected, and this is very, very bad. Why? Because to create an ultrasound image, we want ultrasound to be transmitted. As we applied a gel in place of air, most of the ultrasound was absorbed or transmitted. As you can see, the value is 0 here. So you will further write here that when gel was applied, alpha became 0 and most of the ultrasound was transmitted. Simple as that. Let's further move ahead. Let's also see the marking scheme. Yeah, you can see here this is written. We got 0 correct. 3 significant figures पे we got 0.99 as correct value. However, if you want to give it till 2 significant figures, I have also told you about that as well. Ultrasound is used to produce diagnostic information about internal body structures. Okay. Explain how ultrasounds are detected. Okay, now we have to explain how ultrasound is being detected. Very, very easy. Ultrasound waves strike, or you can say hit, the piezo electric crystal. They strike or hit the piezoelectric crystal, and crystal. As they hit the, as they strike would be a better word, I would say. As they strike the piezoelectric crystal, the crystal changes its shape. The crystal changes its shape, producing EMF. This EMF gets detected and gives us or provides us information about the ultrasound. This EMF gets detected and provides information about ultrasound. Simple as that. About ultrasound. Simple as that. And alternating voltage V varies with time according to this. Okay, voltage is varying according to time with this given equation. Okay, this is basically an alternating current equation. We have studied this in chapter number 10. The voltage is applied to an ultrasound probe. Okay, the RMS voltage is this. The frequency of the ultrasound is this. You have to determine the value of V naught. Okay, you have to determine the peak value. How will you determine that? Very, very easy. You know V naught is equals to VRMS. One second. VRMS is equals to V naught divided by under root 2. We have studied this in chapter number 10. Let's multiply these two values. VRMS multiplied by under root 2 is equals to peak value. What is your RMS value? 66 multiplied by under root 2 gives you your peak value. Let's do that. 66 into under root 2. This comes out to be 93.3. 93.3 volts. Simple as that. You have to calculate W as well. How will you calculate W? You know W is equals to 2 pi F. What is the value of F? 4.3 into 10 raised to the power of 6. What does this come out to be? 2 pi into 4.3 into 10 raised to the power of 6. This comes out to be 2.7. 1 second. 2.7 into 10 raised to the power of 7 radians per second. Okay, let's check in the marking scheme as well so that I have done no errors in the calculation. Yeah, that's perfect, correct. Let's move ahead. Table 9.1 contains information about air and soft tissues. Okay, air and soft tissues information. Determine the unit for a specific acoustic impedance value shown in table 9.1. Okay, so we have to determine this unit. How can we do that? See, one thing is that you can remember the units. If you remember the units, then they are very easy. kg m minus 2 s minus 1. But let's say you forgot the units in examination. You will apply some AS knowledge here. kg m minus 3 multiplied by the speed, that is m minus 1. Okay, this becomes what? kg m minus 2 s minus 1. Simple. Okay, let's further move ahead. Calculate the density of the soft tissue. Okay, you have to calculate this value, density of the soft tissue. How will you do that? Z of soft tissue is equals to what? Density into speed. So Z of soft tissue is 1.7 into 10 is the power of 6. Speed, we know that is 1600, and density is rho. So 1.7 into 10 is the power of 6 divided by 1600. This comes out to be what? Density comes out to be 1063. So we have to give your answer till 3 significant figures. So let's do it 1060. Okay, let's further move ahead. Use the data from table 9.1 to explain why ultrasound cannot be used to produce an image inside an air-filled cavity such as lungs. Okay. Why can't ultrasound be used to produce an image of the lungs? Let's see. So here you can see the specific acoustic impedance of air is, let's say, 4.3 into 10 raised to the power of 2. For the soft tissue, it is 1.7 into 10 raised to the power of 6. Can you calculate the intensity reflection coefficient here? Yes. Z2 minus Z1 whole square divided by Z2 plus Z1 whole square. Let's calculate this ratio. So 1.7 into 10 raised to the power of 6 minus 4.3 into 10 raised to the power of 2 whole square, and let's divide it as well. 1.7 into 10 raised to the power of 6 plus 4.3 into 10 raised to the power of 6 whole square. Let's calculate this alpha. 1.7 into 10 raised to the power of 6 minus 4.3 into 10 raised to the power of 6 whole square divided by 1.7 into 10 raised to the power of 6 plus 4.3 into 10 raised to the power of 6, sorry, 4.3 into 10 raised to the power of 2 whole square, and let's see what the value is coming out to be. The value comes out to be 0.99. Okay, so why is a value of 0.99 of intensity reflection coefficient bad for us? Why is this value of intensity reflection coefficient bad for us? Because this tells us that if we strike ultrasounds, let's say, let me draw a very weird lungs here. Let's say these are your lungs. Let's say these are your lungs. This is your air. Let's say if we apply an ultrasound here, this is telling us that 99% of this ultrasound will get reflected and nothing will get transmitted inside the lungs. So no image will be formed. So how can you frame your answer here? You can say that alpha or specific or intensity reflection coefficient is too large. Hence, most of the ultrasound will get reflected. Simple as that. And no image will be formed. And no image formed. Simple as that. Let's further move ahead. Let's move on to the next question. As you can see here, we have the same answer. A piezoelectric crystal, okay. Piezoelectric transducer containing a quartz crystal is used to obtain diagnostic information about internal structures, okay. Describe the function of the quartz crystal, okay. What is the function of the quartz crystal? To generate and detect ultrasounds. Now, how does it do that? The vibration, okay, so we can initially start it like this. The quartz crystal is provided with an alternating EMF, and this causes the quartz crystal to vibrate, and generate ultrasound. Now here you can see this is a 3 marker question, so you have to tell about the detection of ultrasounds as well. When ultrasounds strike the quartz crystal, they vibrate, and or you can say when reflected. Here you can add a word of reflected as well, so that examiner will appreciate this. When reflected ultrasound strike the quartz crystal, they vibrate and generate alternating EMF. This causes detection of ultrasound. Simple as that. Let's move on to part B, I1. Define a specific acoustic impedance. We have already studied that. Product of density of a medium and speed of ultrasound in that medium. Simple as that. Let's move on to part B, I2. Describe qualitatively how the specific acoustic impedances of two materials affects the intensity coefficient, okay, intensity reflection coefficient at the boundary. So first of all, let's write this formula that we have been using since ages. Z2 minus Z1 whole square divided by Z2 plus Z1 whole square. Okay. If Z2 and Z1 are roughly equal to one another, what will happen? Your alpha will equal to 0. And what will happen then? Most of the ultrasound gets transmitted. Simple as that. However, Z2 minus, okay, if Z2 minus Z1, like if the difference is very large, like if the difference between Z2 minus Z1 is very large, then alpha approaches 1, most of the ultrasound gets reflected. And this is a situation that we don't want. Let's move on to the next question. Okay, yeah, I have already written this answer for you guys so that the time doesn't get wasted for you guys. Let's read out this question and let's read out this answer, a very journalized answer. Outline the use of ultrasound to obtain diagnostic information about internal body structures. Okay, so how are ultrasounds used to obtain information about internal body structures? What do we do? Ultrasound pulse are generated by the vibration of quartz crystal. Gel is applied to the skin to minimize reflection. Okay. These ultrasounds hit the surface boundary and get reflected. The reflected ultrasounds are detected by the quartz crystal. Okay. The time delay between the generation of electrons and detection of ultrasound tells us about the depth. So there are two things which ultrasound tells us. One is the depth, and how do we get to know about the depth? By the time delay or interval between the generation and detection. What is the second thing we get to know about ultrasound? We get to know from the ultrasound the intensity of the reflected wave. This gives us information about the nature of the boundary. Simple. So let's further move ahead. Okay, let's see this question. By reference to an ultrasound wave, explain what is meant by specific acoustic impedance. We have done this 1,000 times now. You can copy the definition from the above questions. An ultrasound wave is incident normally, okay, on the boundary between two media, okay. The media have a specific acoustic impedance Z1 and Z2, okay. State how the ratio of intensity of ultrasound reflected from the boundary divided by the intensity of ultrasound incident on the boundary depends on the relative magnitude of Z1 and Z2. Again, same answer. If Z1 is equals to Z2, what will happen? Most of the ultrasound will get transmitted. This term, the reflection term, will approach 0. So what will you say? If Z1 is equals to Z2, ratio approaches 0 and most of the ultrasound gets transmitted. Okay. However, if Z1 minus Z2, if the difference is large between the two values, is large, ratio approaches 1. Okay. If the difference between these two values is large, what will happen to most of the ultrasound? They will get reflected. This value will approach 1. The entire ratio, I guess, will approach 1, not this value. The entire ratio approaches 1. Hence, most of the ultrasound gets reflected. Simple as that. Let's move on to part B, I1. State what is meant by attenuation of an ultrasound wave. Loss or reduction in amplitude. Simple as that. Okay, let's see this. A parallel beam of ultrasound is passing through a medium. Okay, the incident intensity is I naught, is reduced to 0.35 I naught on passing through a thickness of this value of the medium. Calculate the linear attenuation constant mu. So do you remember this equation? I is equals to I naught E minus mu x. What is your intensity after passing through the medium? 0.35 I naught. What is your intensity initially? I naught is equals to E minus mu x. What is the value of x? Thickness 0.046. I naught guys cancel out. 0.35 is equals to E minus 0.046 mu. Now take ln on both sides. What will happen? ln 0.35 is equals to ln E minus 0.046 mu. ln E gets cancelled out. And your answer for mu comes out to be ln 0.35 divided by minus 0.046 is equals to mu. Let's calculate this answer. ln 0.35 divided by 0.046. This comes out to be 22.8 meter minus 1. So this marks the end of past paper for ultrasound. If you have any questions, you can ask in the comments. This PDF is uploaded on the Google Drive, which is linked in the description below.